Let's elucidate a geometric visualization of the quantum search algorithm. Previously, we introduced the oracle omega, which distinguishes targets from non-targets. N is the total number of targets and non-targets. C is the total number of targets. If C is equal to 0, then there are no targets. If C is equal to 1, then there is a single target among n elements. If C is greater than 1, then there are multiple targets scattered among n elements. The angle theta is defined in terms of the ratio of C and n. Targets can be represented in binary notation as L-bit strings. The aim of the quantum search algorithm is to search for C targets among n elements. To perform the quantum search algorithm, we need to prepare an L-qubit register in a state that approximates the target superposition. Three different ways of expressing this quantum state are shown. First, on the left, we can see an expression that emphasizes how to prepare this quantum state. Then we can see a shorthand notation for this quantum state. And finally, we can see an expression that is a linear combination of the orthogonal superposition and the target superposition. The coefficients in this linear combination are trigonometric functions. The argument of these trigonometric functions depends on the angle theta that is defined in terms of the ratio of C and n. Q also appears in the argument of these trigonometric functions. Q is the number of iterations of the unitary operator U. So we need to apply this unitary operator U Q times to prepare this quantum state. And if we apply it Q times, then we're going to get an approximation. So this linear combination is going to be approximately equal to the target superposition. And the target superposition is a uniform superposition of the target L-qubit computational basis states. In total, there are C of these target L-qubit computational basis states. So this procedure is actually amplitude amplification. We're amplifying the amplitudes associated with these target states. And that means that the other states, which are non-target states, and they can be found in this orthogonal superposition, their amplitudes are getting reduced. So they're going to have negligible probability amplitudes. But these target states are going to have amplified amplitudes. So now when we prepare this state which approximates the target superposition, we can perform a measurement. And we're going to measure the L-qubit register in the computational basis. So we will have a large probability of measuring one of these target L-qubit computational basis states. We need to repeat this preparation and measurement procedure until all target states are measured. And here you can see two different notations for these target states. We have a condensed notation with a superscript L that reminds us that these are L-qubit computational basis states, which are labeled by these little t's. Those are elements of the set T. They are targets. And over here, what we have is a more explicit notation that shows individual qubit states. And the labels of these individual qubit computational basis states are actually bits. And these are the bits that appear in the binary representation of these targets. So T sub L minus 1 all the way down to T sub 0, those are all the bits in the bit string that encodes a specific target. And you can imagine tensor products appearing in between these kets. And that allows us to combine these single qubit computational basis states into an L-qubit computational basis state. So this is a summary of the quantum search algorithm. We prepare this state that approximates the target superposition, and then we measure that state in the computational basis. And we have to repeat this procedure until we measure all of the target states. Now let's have a look at this Q. That is the number of iterations of this unitary operator U. So how many times do we have to apply this unitary operator? In the red box, we have an expression which tells us the value of q. So we want to choose the number of iterations so that this approximation holds. And that happens when q is the floor of pi over 2 theta. And theta can be rewritten in terms of this ratio of c and n. So that means q needs to be the floor of pi divided by 4 times the inverse sine of the square root of this ratio of c and n. And this quantity is bounded by the quantity which is the ceiling of pi over 4 times the square root of n over c. So inside this square root, we now have the reciprocal of the ratio. So this is n divided by c. It's not c divided by n. And this is an upper bound on this quantity over here. So that means that the number of iterations is bounded by a quantity that grows like the square root of n over c. And this property over here is actually the reason we're considering the quantum search algorithm. This means that it provides a computational advantage compared to classical algorithms. So this is a very important upper bound over here. And in the special case where we're only searching for one target, we can set c equal to 1. When c equals to 1, this is bounded by something that grows like the square root of n. And n is actually the search space. It's the number of targets and non-targets. So it's the total number of all of the elements in the search space. So that means that the number of iterations is bounded by a quantity that grows like the square root of the search space. This is a very important property of the quantum search algorithm. Now let's have a look at some reasoning as to why this value of q is required. So when we want this approximation to hold, we want this linear combination to be approximately equal to the target superposition. So let's have a look at these coefficients. We need this cosine coefficient to be approximately equal to 0. And we need this sine coefficient to be approximately equal to 1. That happens when the argument of these trigonometric functions is approximately equal to pi on 2. So cosine of pi on 2 is 0, and sine of pi on 2 is 1. So that's the ideal case. But in general, we're not going to have an exact equality. This is just going to be an approximation. So it's amplitude amplification. We're not guaranteed to have a 100% probability of just measuring targets. There still might be non-zero probabilities associated with the non-target states. But this is the approximation that we're looking for. So the argument, which is theta times 1/2 plus q, that needs to be approximately equal to pi on 2. And if we rearrange this expression, we can divide both sides by theta, and then we can subtract 1/2. And that gives us this approximate expression for q. So q needs to be pi divided by 2 theta minus 1/2. So if we take the floor of pi divided by 2 theta, that is going to be approximately this value. So remember that q is the number of iterations. So it has to be a whole number. It has to be an integer, a positive integer, in fact, because we're applying this either 0 times, that means we're not applying the unitary operator at all, or we're applying it 1, 2, 3, or several times, however many times we need to guarantee that this approximation holds. So this needs to be a positive integer. That's why we're taking the floor of this. So this notation over here is for the floor function. And we have a floor function over here on the left-hand side, and then this upper bound is actually the ceiling function of this quantity. So we need to put these floor and ceiling functions to ensure that we're dealing with integers. So that's the reasoning in this purple box, and that's helping us see why we need to choose this specific value of q. So in the green box, we saw a summary of what was covered in the previous video about the quantum search oracle. And now in this blue box, we've seen a summary of the quantum search algorithm. And in the red box, we saw how many iterations are required to implement this approximation over here. And that procedure is known as amplitude amplification. So now we're ready to construct some matrices, and these matrices are going to help us create a geometric visualization of the quantum search algorithm.